Welcome, everyone. So, like Patrick said, right? I'm going to talk about a topic which the reason I chose this topic, just so all of you understand, right, is that I'm seeing a trend, an upward trend in the industry as well as in academia for knowledge graphs. It's not like they're new or they're immediate, something that's come up in the recent years. They've been around for a while. I feel that now we have enough data and enough, power in terms of hardware as well as the foundation models. So they're becoming quite popular. So with that, let me share my screen and we'll get started. Uh, Patrick, are you able to see my screen? Perfect. Great. All right. So, all right, so you know the topic. This is what was talked about, and so the first thing I'll start with, as in any system, as I'm sure a lot of you already know, all of you know, right? You have to think about what's the input and what's the output, right? So in our case, from a data science perspective, the first question is, okay, like we're talking about graphs and knowledge graphs and so on. So what's the data that's put in? So in a graph database, you can put in different forms of data. A very popular form, which is also very popular in the industry, is a JSON. So, if you know, most of you already know what a JSON is, but you see an example on the right. It's basically kind of structured, semi-structured data. It has name value pairs, and then it has hierarchical. So you know that there is a document that has a particular number with the date, and then within the document, these are the lines that are part of the document. So that's how a JSON is represented. And you can take that JSON and push it into a graph database. Well, what does that do? So I'll go to key steps number 3. So there are all these different commercially available and also open source, some of them loaders that will take the JSON and then create a graph database out of it. Essentially, what these loaders do are they will identify the entities. Entities meaning those are the nodes. So everyone just think of a graph. You have nodes, which are the circles, and then you have relationships that are represented by lines or edges between those circles, between the nodes. So what the loader will do is that it will identify the entities, in other words, the nodes of the graph, and then it'll also identify the edges or the connections, the relationships, right? Now, why is this interesting? The reason it's interesting is that, as you can imagine, in today's connected world, um, you know, there are a lot of relationships between data that you would like to traverse, understand, and derive insights. More often than not, those relationships are not that easily expressible in a database table. So that's where graphs are really powerful. We'll go into that a bit more. So now, once you have loaded the data into a graph database, I know we want to talk about knowledge graphs. So how do you go from a graph database to a knowledge graph? Or what's the difference? You can think of it as like the graph database is the technical, it's the nuts and bolts, it's the underlying technical storage, it's the engine that is storing the data. And the knowledge graph sits on top of it. And the knowledge graph is the one that creates all the semantics, the functionality. It's basically the one that connects the meanings between the different nodes. Okay. Um, I work with a team, and someone on the team came up with this phrase connected intelligence, not collective. Collective intelligence, it's already a popular phrase. But they came up with the name of connected, this phrase connected intelligence. And I really like it because it's very apt and very suitable from a knowledge graph database perspective. Okay. So essentially, what we are talking about is that you have data, you are going to convert that data into JSON, and you can look up, it's not that difficult to convert any data. If you have a CSV, if you have some, unstructured data, you can always create JSONs out of it. From that JSON, you basically create some ontology and mapping. What's an ontology? What's a mapping? Exactly what we talked about. Like the loader will create these, will detect the entities, will detect the relationships, right? That's what the ontology mapping is. And then that gets loaded into a graph database. And sitting on top of the graph database is a knowledge graph, right? So the graph database is the underlying technology. That's the storage. And the database, it's a knowledge graph. Okay. So just a very simple visualization is you have the JSON, you create the ontology, the rules, and then you get into a knowledge graph. Okay. Now, that's where we are right now. So we started with some data, we converted it into JSON. Now we have a knowledge graph. And the knowledge graph, I mentioned this briefly earlier, it has a lot of advantages, right? Especially with regards to a traditional relational database system. That's what RDMS is, a relational database management system, which has a lot of tables and you have different relationships between the tables. So definitely a knowledge graph has a lot more flexible schema. In a relational database table, the schema is it's set. Schema means the columns of the tables. So that's set. If you need to change it, you have to migrate the tables and so on. Um, Relationships often, if the relationship is within a table, then of course you just work with a particular table in an RDMS. But if the relationship is across tables, then you have to do a little bit of joins, right? Bring the data from multiple tables together. In a knowledge graph, the relationships are the key. That's what gives us the connected intelligence, right? And of course, in an RDMS, like hierarchies mean you have to do a lot of joins, but those are a lot simpler to pull out in a knowledge graph, primarily because of the way the data is represented as a graph database. So you have connected nodes, edges. Um, in a cross-domain integration, if you are trying to connect unrelated tables, it's difficult. It's not impossible, but it involves a lot of work. In contrast, with the knowledge graph, you can always put in data into the same graph. You can put in data from different functionalities, different, say, business verticals. Okay. And in a data discovery, for a relational database, you really have to create queries, meaning you're querying the database, like using, say, a structured query language, SQL. In contrast with a knowledge graph, once you traverse the graph, you can discover relationships. You can understand, like who is buying what, which products are being sold in which areas. So you can traverse the graph to do these discoveries. Okay. So in a knowledge graph, what the way I started today's call, right? There's a lot of momentum now with knowledge graphs in the industry. There are a few primary reasons other than the technology side. The first one is it's breaking down silos, of course, because the what we looked in the previous slide. It's easy to put together functional data in a knowledge graph. Okay, so from that perspective, it connects the data across different functionalities, and it makes it a lot easier um, to connect, view such data together, which otherwise would not have been possible without a lot of heavy lifting. So it enables a unified real-time view, often of an enterprise or an organization or a business landscape, right? The next thing is that because you have this connected data, you can often get instantaneous actionable insights, right? And that fuels a lot of the analytics. So you can make faster decisions. You have those actions that are immediately becomes apparent because of the connected across the different silos. Once you have this connected data across different silos that is driving your analytics, essentially what you're doing is that you're future proofing the enterprise. So, what do I mean by future proofing? When your organization, when the company is now going into new geographies, releasing new products, entering new markets, because you have a flexible way to represent the data using a graph database, you don't have to reinvent the wheel. You can just leverage what you currently have, connect to it, and then all the analytics that you were using previously just works. And that, enables AI driven leadership. I mean, AI, as you know, has become a big buzzword and is a big driver, in industry right now. So future proofing the enterprise enables, good decisions, and also enables AI leadership. Okay. And a domain knowledge graph is a knowledge graph specific to a domain. We'll see some examples, but a domain, what I mean by a domain is in the industry parlance, like a vertical, like healthcare, retail, manufacturing, finance. Those are all the verticals. So if you have a domain knowledge graph, it it really powers, like it's like a turbo boost for the enterprise in that domain. Okay. Um, just continuing on that, from a knowledge graph perspective, you get a 360-degree view. If you have clients, a lot of organizations do, you get a holistic client insight that is enabled because you're able to break down the silos as well as accelerate the data value chain those are the ones we saw out here. So those are the symbols at the top that's repeated on this slide. You also are able to derive a lot of insights, right? Like, so that enables AI driven leadership. And the reason is because you're unifying the data not just from different functionalities but also from different legacy technology systems, right? Not just legacy, but different systems that have important data, but those systems work in different parts of the organization, of the enterprise. So you could have a CRM, like a customer relation management system. Web analytics maybe is stored in some other repository, and a graph database can bring all of this together, right? Once you're able to do all this federated search, right, it really pushes the AI-driven organizational change. And the other thing with the knowledge graph is that with the data ingestion that we saw, right, you're able to pull in new products, new KPIs without damaging or without breaking any existing analytics that's running. And existing analytics, going to point number 4, that's not only able to give you new discoveries, but you're also able to personalize the offerings. And that's the key, as you may already know, right? The industry, with the power of generative AI, is moving more and more towards personalization. Can I reach out to you with content, with products that you as an individual are interested in, right? That's the key, right? That's what the industry is moving towards. And then, once, how are we going to get to the personalization? We need more data, right? More interaction with the end user. And one of the ways to get all that data, improve the interaction, is to have more AI assistants, right? Have more interaction. So it's that way you can scale. It's not just individuals. Of course, you want to have human to human touch points, but you also want to scale that with multiple AI assistants. And having a graph database really empowers you to scale that across the enterprise. Okay. Um, from an implementation perspective, so everything sounds good, right? Like we talked about data ingestion. Now we have a knowledge graph. We understand the power of the knowledge graph. Now, from an implementation approach, right? The first thing to do would be to understand, like in your vertical, right, what are some of the nodes, the concepts that form, that your enterprise is interested in. Are you selling to individual retailers like you and me? Are you selling to, say, finance? You're selling to some advisors in trading companies. Are you selling to hospital physicians, Who are you selling to, right? Then from there, you go to point number two, which is you select a particular use case. Now you have your ideal customer profile, you know who you're targeting, you know what you're targeting with. Then you start looking at the data. You load the data. Once you have the data in point number three in a graph database, right? Then you start going into knowledge extraction. You know, extract the different entities, right? Extract the relationships. Once you get those extractions, right, then you're able to demonstrate the value because now you have the insights and you then apply the insight back to your point number two, point number one, that this is how you are making a difference to your target customer, to the target person, or the target organization. Once you're able to demonstrate value at a smaller scale, then the next thing is to validate that, make sure that that is actually working. It's demonstrating value for the business. Then you just scale it. You scale it across maybe more users. Maybe you scale it with new domains. You go enterprise wide. All of the different ways to scale this. Okay. Now, note, this is only based on the knowledge graph, right? So, what are some actual industry examples, right? So, these are some of the examples. Again, these are all, available. Like, just pulled some examples out. So, Morgan Stanley is, you can see it, they build a knowledge graph for compliance and analytics, which again is a very powerful use case, right? As you know, finance is a highly regulated industry, highly regulated vertical. So they have it out there. Then the next one is Banco del Peru. They pushed their insurance sales through graph-driven personalization. Again, we talked about it, how you can use the knowledge graph to personalize the offering, right? And something that we will see an example of fraud detection. Knowledge graphs are very powerful for fraud detection. Why? Because fraud often has relationships, right? You have maybe one entity which is committing fraud across different locations. If you're able to put that in a knowledge graph, that entity will light up like a Christmas tree, right? So you're able to do all of that with the knowledge graph. And then some more industry use case. If you don't know Elevance Health, they're like one of the biggest Blue across the country, and an health insurance provider. They also hyper personalize, healthcare, so they know exactly what product in terms of which insurance to offer to different individuals, to retailers like you and me, right? We all know eBay does a lot of recommendation using graphs database, and of course Walmart, again, context aware product recommendations. And these are all being powered by a knowledge graph where they're taking advantage, leveraging the relationships between different entities. Okay. Just I think the last thing on in this section is that if you think of a client in an investment bank, that client has a consultant from the bank, and the different ways that a knowledge graph within the bank can help is that now you can have a 360-degree view of the client in terms of how many interactions have different consultants in the bank had with that client. What is the client interested in? The last time we spoke to the client, what is the competitor doing? What's the competition doing to try to woo the client away from this bank, right? That's also, you can embed that in a knowledge graph. What are the client details, right? That's in the individual, in the bank's data warehouse, the DW. What are the financials of the client? What are some of the products that the client is currently using, right? That is also good to know, so that when you draw market intelligence, you can compare what are some of the other products that others are using, right? Comparator intelligence. You can only do that because now you have this graph database that is connecting the edges, and it's saying, oh, you know what? Client John Doe or Mary Jane is worth this much and is using this particular product. Now, the same product or a similar product is also in the market and is offered by one of our competitors. Now, all these, right, and it goes on. You have consultant relationships, direction, pipeline, meaning what else are we talking to the client about? Now, instead of going to different systems, now all this data, by the way, is in the enterprise. It's not that its data is missing, it's just the question is how do you connect all this data to get a 360-degree view of the client? That's what the power of the knowledge graph is. And then, of course, now you can use knowledge graph with Gen AI. So how do we do that? Before I go into the details, this is a hype cycle for Gen AI. Gartner is an organization that publishes this. And what's interesting out here is that you'll see that where we are, in terms of the peak of the expectations, you can see a graph rag. I think most of you know what a RAG is. It's a retrieval augmented generation. It's a very popular design pattern for Gen AI in the industry. And what people are moving towards is not just RAG, but pulling that information to be utilized in a generation, right? The retrieving from a graph, a knowledge graph. So that's what a graph RAG is. And that's what, just to tie it back to what I said earlier, that we are seeing this a lot in the industry, right? A lot of, if organizations are already using knowledge graphs, they're doubling down. If they're not, they're pushing, they're thinking about how can we bring all this connected intelligence together. Now, this is a picture that I generated. If you look at the icon on the bottom right. I use Gemini, and I don't know if you know about this. They have something called a nano banana, so it generates really cool pictures. So I thought I'll try one for this talk. Now, this is using Gen AI. If you remember, I talked about how you take different data sources, right, which are and then convert it to JSON, and then you map entities and relationships. Well, one way to do that is using a loader. Another way is that you map those entities and relationships using a foundational model, using GenAI. So you can ingest unstructured data sources as well as structured data sources into a GenAI engine, and then ask that engine to generate a graph database. Okay, or at least the code to load it into a graph database. And an example of that would be, you can see this example. It's a Google-based example. It's about the CEO of Google. You have structured data on the left. Different types of structured data. You have a JSON at the top. You have some structured data, which is like in a tabular format on the left. And on the right, you have the unstructured data, which are just analyst reports or reports on Google or investor call transcripts. You put that into Gen AI, and then out comes the knowledge graph code. Okay. So this is an example of leveraging Gen AI to ingest the data. So that's on the ingestion side. You can also leverage Gen AI, as we mentioned, right, on the graph rag side. So what does that look like? You have a query coming into an LLM. Now that query is converted to a graph query. That graph query is now sent to a knowledge graph. From the knowledge graph, you retrieve the relevant subgraph, right? And then that is used by the LLM to generate the response. So in a traditional RAG system, this knowledge graph would be represented by a vector database, but now you have a graph database, a knowledge graph writing on top of it, and that's what pulling the information. Similarly, I mean, this is an example from an individual, right? A consumer example. This is a healthcare example where, the physician is asking a question to the LLM, like a clinical assistant. That LLM is now tapping into a knowledge graph that has all the relevant information about this patient. Like what are the different diagnoses for the patient? What are the different diseases for which the patient has been diagnosed with? What are some of the clinical results? So it's all interconnected for that individual patient, which is now allowing the LLM to get a very unified 360-degree view and come up with a response. Okay. Um, so we talked about data ingestion into a graph database. Then we talked about a knowledge graph, the advantages of using a knowledge graph. Then we talked about how Gen AI can be leveraged both at the ingestion as well as the getting the insights out. And one of the biggest use cases of the design patterns is the graph rag, which is now becoming quite popular, right? Next, we'll talk about now that, we'll talk about more on the deriving the insights, right? So you have a knowledge graph, and now, there's this whole field of graph neural networks. Now, what a graph neural network does is that it uses machine learning and deep learning techniques on a knowledge graph, right? So, neural networks that are designed to operate directly on the knowledge graph instead of, and the core idea is that you basically learn embeddings and, that reflect not just the features. So each node in a knowledge graph, and what I mean by a node, I'll just go back. These are all the nodes. You can see the circles, the nodes, and then you have the edges, right? So a node can also and will also have features in it, right? So a graph neural network not only learns the features that are present in the nodes, but it also learns the neighbors of each node. In other words, the connectivity, the relationships, which are very important, right? And you have different variants, convolution graph neural networks called GCNs, then Graph Sage. I'll show you an example using a graph attention network. So that's a GAT, and then there's other ones, message passing, so on. So just some details on them. A graph convolution, what it does is it aggregates the neighborhood around a node, right? And it normalizes that. So what I mean by normalize is that you may have some nodes that have a lot of neighbors, highly connected. You have some nodes that are really isolated, maybe one or two connections. A graph convolution neural network will be able to represent that degree of connection, but it'll also normalize it so that, the numbers are not too large for the highly connected and too small for the not connected. So it'll normalize it. A graph attention network, just jumping to number three, does the same thing, but it uses this concept of attention, which is, as you know, right, very popular and very much used in transformer architecture. All your GPT and all of them, which use the decoder part of the transformer, they all have attention built into them. So a graph attention network does something similar. Graph Sage, it supports it's something that's very scalable, especially for large graphs. Message passing, which is number four, is aggregates messages from the neighbors, right? They get each node, each getting a message from the neighbors and then updating their state. So it's a very flexible graph neural network. And for dynamic graphs, especially for time series forecasting, what's popular is the temporal and spatiotemporal GNNs. Okay. Now, especially in terms of like graph neural networks versus a regular neural network, right? I think a lot of you already know about this, right? It works on regular data, the traditional neural networks. The input and outputs are fixed. In contrast, a graph neural network is designed to work with knowledge graphs. So it models entities, relationships, right? And node ordering does not matter, right? Graph size does not matter. You can keep adding new nodes to the graphs. So their biggest advantage on a graph neural network is that it directly leverages the knowledge graph topology, right? And it also, it enables a lot of reasoning using this neighborhoods of the graphs, right? So about connected intelligence. And you should always think of, or one should always think of graph neural network when your data is inherently relational, right? Like fraudulent rings, social networks, supply chains. When you have a lot of relations between different entities, think of a graph, knowledge graph, and run a graph neural network on top of it, right? Um, the connections are not just attributes, node attributes, but also the relationships, the patterns of the connections, right? Like like this individual or this company supplies this product. That product is sent to these different distribution centers. From there, they're reached to the stores. From those stores, these are the type of consumers. When you have all these relationships, graphs are very powerful. And you also need graphs when you have some dynamic, like things are not static. It's always changing, right? Like new users are being added, new products are being added, new geographies are being added, right? And if you need um, reasoning or you need some kind of insights that's across different geographies, across different products, right? Graphs are very powerful to do that. And they matter, of course, like why they matter. I think we talked about it a lot. It's scalable. You can combine relational learning, good for patterns, right? And they have really demonstrated good outcomes across social networks, relations, traffic. And what I mean by traffic is not just your road traffic, vehicular traffic, even web traffic. Graphs are very powerful for that. And when you use GNNs for enterprise, what it does is it enables, they're also a lot, I mean, they do suffer a bit from explainability, but they are a lot more explainable than, say, large deep learning neural networks. Um, they also facilitate reasoning across entities. We talked about it enough, right? Across different products, different geographies. Easy to combine structured and unstructured data, textual knowledge, with, say, really, with tabular data that's put in a graph. Um, with the neural network, you're able to now do predictions. One of the types of predictions is what is known as link prediction. Often they want to know if a particular node is going to be linked with another node, right? What's the probability of that link happening? Those are some of the things that are used then for recommendation, personalized recommendation, risk assessments. And of course, number five, the biggest thing, you unify siloed enterprise data. For those of you who work in enterprises, you understand there are a lot of data, relevant data, useful data across different technology, different databases, and the graph is a very strong, very powerful way to connect all of that. If you're thinking about getting started in PyTorch, you have Geometric, that's the package, and in TensorFlow, you have GNN. All these packages, libraries are available, open source to get started. On the cloud, again, all three variants, like the three major hyperscalers offer. Amazon AWS does, Neptune ML. You have Cosmos DB, and then Vertex AI also supports uh, graph neural networks. So we'll go to our use case right now. So we talked about, again, we started with the data ingestion, went into graph database, went to knowledge graphs, Gen AI with knowledge graphs. Then on knowledge graphs, we talked about how you can use graph neural networks to get insights. So I'll give you a very simple example with the fraud detection. So it's a fraud detection where the nodes are users. So it's a heterogeneous graph, right? If what I mean by heterogeneous is that each node is not just a user. It can be a user, dollar transaction, merchants, locations. You have edges that I'll show you an example. And we will use a graph attention network, or GAT, to learn embeddings and to predict suspicious nodes, right? So again, GATs are very good fit because fraud always or often is across different hidden connections across different entities. So you want to understand. Remember, a GAT is using attention, so you want to understand which connection to pay attention to, which edge, which relationship to pay more attention to. Okay. And again, it pay attention to fraudulent behaviors and it's scalable. So let me show you the data. This is a very simple data. It's some completely cooked up, simulated data. So you have 10 transactions across four users, U1 through U4. Okay, and you have the IDs for each of those transactions. You have four users, three merchants, and then you have I guess five locations, L1 through L5. And the ones that are, this is labeled data. So this is the data used to train the GAT. And the ones that are marked in red are the ones that are fraud. So that's why the label is a 1. Okay, so 10 data, you create a knowledge graph and then you train them all. So let me show you the knowledge graph. I don't know if you're able to see this properly. I know they're very small, but this is an example of a knowledge graph where you see the circles. Those are the nodes. And if you look at the legend at the top, it'll show you what the nodes represent. So you have a green and the red, they're all transactions, right? The dollar transactions. The red are the fraudulent ones. Remember, we had three of them from here, three fraudulent transactions. The purple are the blue are the users, right? The U1, U2, you'll see them, you see some out here. Those are the users, U1, U5, these are the users, right? The purple are the locations, okay? Locations, and the yellows are the merchants. So you have one, two, three merchants. You have, I think, four users. And anyway, that's how and you can see the edges, right? So you can see, this transaction happened at location L1. So you can see the edge, right? You can see
So,
that this merchant paid
start the
this
start.
particular transaction, right? This transaction made by this user, this transaction made by this user. So those are the edges, the relationship between the different nodes. And then the nodes represent the entities that you see on the top left. And this is a knowledge graph powered by a graph database. And you again, this is the data, and this is how the knowledge graph is created. Now, to get the insights from this knowledge graph, what we do is that we create a graph attention neural network, right? A GAT. Now, attention, like I mentioned, right? What we want to understand is which are the nodes to pay attention to when detecting fraudulent transactions. Now, those fraudulent transactions are already labeled. So the network knows which are the fraudulent transactions. Now, the GAT that we created, and I won't show you it's a long diagram of what the GAT looks like, but the GAT has just two layers, right? Two hidden layers. So what I'll show you next is that for the first layer, which are the edges that the GAT is paying attention to. So when you see the thick lines, those are the ones that it's paying attention to detect fraudulent versus non-fraudulent. So let's first take this one. This is the fraudulent one, the T6. So you can see to get the fraudulent, it's not paying attention that much to the merchant. Instead, it's paying attention to which is the user who made this fraudulent transaction and what's the location where this fraudulent transaction was made, right? In contrast, right, if you look at the non-fraudulent, you see the similar pattern where again it's not looking that much into the merchant, it's looking more at which is the user and which is the location. Now, when it's looking at users, then when you look at a graph like this, you can start thinking, okay, it's looking at users. That means that it's looking at their past behavior to understand if the same user is making multiple fraudulent transactions, right? So then this is layer one. If you look at layer two, you can see what's happening. It's only reinforcing the edges on which it's paying more attention to. And as you might know, right, the reason these are important is because when it needs to predict and you add a new node or you ask it to do some link prediction, and or you ask it to say, like I have a new transaction that's connected with this user and it was made by this merchant and at this location, you know that it's going to focus on the user and the location to make a decision whether it's fraudulent or not, and not put that much emphasis on the merchant. So again, two things to get out of this, right? One is you have the knowledge graph. With the knowledge graph, you can get insights, just understand who is transacting more in which location is hosting which of the users, which merchants, which location is having the higher transactions, right? That's the insight that you just get from the knowledge graph. Number two, when you run a graph neural network on top of the knowledge graph, an example would be an attention network, then you can train the network to then start predicting for future unlabeled transactions. Okay. The last thing I wanted to talk about is graph neural network with Gen AI, right? Like how is that being used? So again, I know there's a lot of sentences on this, but I'll quickly summarize. We talked about graph RAG. So LLMs are using a lot of graphs to understand the relationship, the structures when responding to queries, right? That's the left side. And then the right side, that's what it says about graph RAG. So instead of just isolating vectors, which are kind of like isolated chunks, right? What it's doing is it's getting subgraphs part back from a knowledge graph that actually has the relationships built in, right, for context. And that's leading to more coherent responses. You also have GNNs that are running on top of knowledge graphs to do a structured retrieval that feeds into the LLM. And then, of course, you have a lot of agents, right? And that's right now, a lot of agents are, agents is another very popular uptrend. So you have a lot of tool orchestrating agents that are working with graphs. And then on top of the graphs, you can add a GNN to get the right retrieval or maybe to get a prediction. Okay. So GNNs are really powerful with a RAG. They retrieve it, they will aggregate the context. They also give you some predictions, right? And the final thing I'll say is an example. This is an example from another domain, which is like just supply chain, right? So you have these raw materials that are now being shipped to different factories. From the factories, they go to a distribution center, a distribution hub, and then you have a store, right? This whole interconnect between raw materials, suppliers, factories, distribution, stores, this can be completely put into a knowledge graph. And then, as you can see in the bottom, right, you can have a neural network, a graph neural network, analyze the network topology and run different what if scenarios to say if a failure happens in one of these nodes, if a raw material is not reaching one of the factories, if the distribution center goes down, what's the impact on the whole network, right? And in this example, what happens is that you see there's a real world scenario where a disruption is being detected. And again, this is simulated, right? A disruption is being detected, factory B experiences some capacity reduction. Then using the data from the GNN, what the Gen AI can do is then it can plan mitigation strategies. So it does a planning. As you know, LLMs do a lot of these plannings, right? So once it does the planning, then you can have agents that all go take that plan and execute. So an agent could be, executing, like rerouting some of the products from the factories through, or the raw material to the factories, maybe routing some more towards factory A because factory B is experiencing a capacity reduction. All in all, to minimize the disruption and the impact of this factory B capacity reduction. All right. So that is, that's primarily what I wanted to share with you. I know I mentioned at the beginning, right? Collective intelligence has been around for a while and it is very closely related to connected intelligence. So I thought I'll end with this quote. which is, it's the capacity of human collectives to engage, and to create, innovate in a cooperative manner. That's what a knowledge graph enables us to do. So with that, Patrick, I'll hand it back to you.
Yeah, thank you, Dr. Bose. We really appreciate it. Thank you so much for your presentation. We have about 13 minutes left, so we cut it close, but we like to open it up for some questions. Please utilize the hand raise feature for that. And yeah, we'll take questions through 6 o'clock. Thank you. Charlie, you can go ahead.
Thanks. So I had a question about the way that knowledge graphs are built. So it seemed like the rate limiting step of building or using knowledge graphs was making the schemas and definitions, and you said how AI helps with that. I'm
Yeah.
wondering, how trustworthy can we be with AI with building those knowledge graphs? And then, like, if there's another rate limiting step to consider now that AI is here to help us with that.
Yeah. So the first answer, right? Like, we all know the limitations, right, of Gen AI, especially, right? Like in terms of hallucinations, right? So you always have to be very careful about that. So, you can think of it like you always have a human in the loop. The question is, is the AI leading or is the human leading, right? So in this particular example, where the Gen AI is helping create the relationships, the entities and the relationships, I would say it's AI led, but always reviewed human, right? So you always have that. So in a way, that could be a limitation because at the end, right, you can only review that much, right? Like how fast you can go. Um, Other rate limiters, you always have, scale is always an issue, right? Like it's the knowledge graph that I showed you, it's so much, it's really fast. It has only 10 entries. It runs in a blink of an eye. If you scale that to 1 million, which is easy data for an enterprise, right? So you have to really consider the engineering aspect of it, like how to make it such that it can run fast and your queries are not taking a long time. So that would be the scale is the biggest limiting factor.
Thank you.
Thanks, Charlie. And Lucas, you're welcome to jump on with your question. Thank you.
Yeah, so thank you very much for the seminar. It's very interesting. Assuming I already have a vector database and a reg system, what would kind of be like the simplest, proof of concept that I could build for a graph database and, extract insights from it? Like, is there a way to already kind of leverage the similarity information that I already have from the vector database or anything like that?
So that's a good question. That I'm reluctant to say that you can go from a vector database to a graph, right? If you have the original data, I think it will be better to go from the original data to the graph. And the reason I say that is, as you know, right, like when you have a vector database, you already made some assumptions about how to do the chunking and how to create the vectors, right? So maybe, like you can, to your point, right? Maybe you can, I'm just saying, right? Like if you don't have the original sources, maybe you can start thinking of, within a vector, maybe create some metadata and put the vector as a feature and the metadata as the nodes, right? And then create the relationships. But you're then limited by the assumptions that you made to create the vector database. In
I
contrast,
see.
if you go straight from the source, right, you'll really leverage the power of a knowledge graph, if that makes sense, right?
Got it. Yeah.
So,
So just as a quick follow-up. So, yeah, assuming I do have the documents and the chunks and everything.
yeah,
So in that case, the ideal way to start would be, as you showed, that, start defining ontologies, establishing the relationships that would be
yes.
interesting. Okay, got it. Okay.
Yes, exactly. Find out what you're looking for in those documents.
Mhm.
Just a simple thing, right? Like if there are, like, say, company documents, right? And I'm just creating a silly example, right? Like Apple, Microsoft, and all that, right? So definitely those are your entities, right? Now, what do you want to do with those entities? Are you thinking about, like, is it like, like who is announcing which, like their quarterly report, right? Like, how is the trading going on? So then those give you ideas of the further nodes and then the relationships between them, right? Those, those are the things.
Got it. Thanks a lot.
Sure.
Charlie, we're happy to hand it right back to you if you have a question. Go ahead.
Yeah, I had another question. This is related to the how you mentioned that for better products, you need more interactions, more data for the AI. In fraud detection, you can detect relationships, and that's going to be helped with more interactions and more data. I'm wondering about the ethical side of it and how we can work on improving that. Because for the fraud detection, it's like 99.9% of customers probably aren't committing fraud, like for a bank. But then, like, for that 0.1% for like that detection aspect, what time, at what point does like that data collection become unethical?
Oh, so when you say unethical, uh, just so I understand, I think what you're referring to is that you're collecting data from other individuals who are basically not engaging in fraud, right? But that's what you're saying. So
Right.
often what happens is that, the data that you're collecting is not just for a fraud transaction detection, but it's because, say, you're a merchant or you're a bank and you are going to collect those transactions, those data for regulatory reasons, right? Because all of them have to collect it. So even when you are, say, using your credit card, right? If you use a credit card today evening, that data is being collected somewhere, right? So then the question is, on top of that collected data, can you run some algorithm to detect fraud? That's the way. So it will be less of I'm using the data only for fraud. It's more about, like now I have the data. Let me create a knowledge graph. One of the use cases of the knowledge graph will be fraud detection.
Okay, got it. I have another question, but I don't want to like
Sure.
step on any other like questions. But so I have received criticism from a manager about not mastering knowledge graphs and not going in deeper with this. And so I'm wondering what mastery over knowledge graphs looks like. Is that knowing how to use it in the future, knowing what use cases it has, maybe like the history of what it's fixing or what it's improving? Um, so I'm wondering if you have any insights for that, or maybe any facet of data science, of becoming a master or expert over it.
Yeah, it's a broad question, as you can understand, right? Like the person who gave you that feedback must have had something in mind, right? Which you were so. But having said that, if someone comes to me and says that, like they know everything about, they need to know about knowledge graph, right? One of the things that I would ask is that, okay, give me a use case where a knowledge graph is giving me more in terms of what I want to get my business end goal than a regular database. Or in contrast, like the discussion I was having with Lucas, right? Or what a vector database is not able to give me. Give me those use cases, right? See, once you start with the value proposition, which is the tip of the pyramid, right? Everything else then falls into place because you have already demonstrated to me that you understand when and why you should use a knowledge graph, right? Then after that, it becomes more like a transactional. Then I can ask you, oh, okay, that makes sense. So now tell me, how would I do a knowledge graph? Then you'll say, you can load it, you can use Gen AI, you can use a loader. Okay, what else can I do with a knowledge graph? Well, you can run a graph neural network on top of a knowledge graph and get more insights, right? But I think, to your point, right? Like if you start with that use case that look, it's not just a shiny new, or not new, but a shiny object that I'm running after. It's something that's important, which is covering or compensating the lack with the current technology, right? A gap in the technology that I'm filling with a knowledge graph. That's a very powerful proposition.
Very good. Thank you.
All right. Do we have any? Oh, we have one more question in here, Dr.
Hey,
Bose.
Tom.
Yep.
Yeah, it's
Are
good
there
to good
books
to
about
hear
the
from you.
topic?
Yes. Um, so Tom, I mean there are books on knowledge graph, right? Like I don't have any too specific to recommend. But there are unfortunately no specific knowledge graph book. I I again, there's no financial incentive for me to say this, but I will say there's a book that I last read, which was from PACT, if you know about them, and it was hands-on graph neural networks using Python. So it was less on knowledge graph, more on graph neural networks. But I thought it was a reasonable book because it talks about all the different flavors of graph neural networks and how to use them. And because it's hands-on, it has a lot of examples, and it has also a GitHub, which to me is always very important because then you go through the theory and then you can practice it. Yeah, absolutely, Tom. Thank you.
All right. I think we're just about at time. What we do want to invite everyone to do is if there are any additional questions that you maybe had for Dr. Bose that come up later, please feel free to reach out to our team in enrollment management. I left our email there. We'll be sure to get them over to Dr. Bose. But we want to thank everyone, especially if you're a currently attending student and you're on break, you're a prospective student, or you're working with an institution and you're on break. We really appreciate your time. And of course, thank you for joining us in the evening. And we will be having data science seminar number 11, probably within the next couple months. So thank you again so much, Dr. Bose, for your time this evening and for everybody coming out. So have a good one.